So, can you take some questions from the block diagram related?
Sorry.
Can you please discuss some questions related to block diagram,
Yeah,
like
we are going to
feedback?
discuss block diagrams only today.
Okay, sir.
Yeah. So, good evening, everyone. Welcome to this live session on 3rd July 2026. Okay. So, we are in week 3 now. Okay. So, week 3 in the previous live. Okay. So, we discussed transfer function and stability also. Okay. So, these are the two topics we discussed, and today we are going to discuss this block diagram technique. Okay, so particularly in stability, we have two kinds of stabilities. So BIBO stability and exponential stability. Okay, so if you're having any questions, you can ask me. So uh, in the previous slide, clearly I've explained what is exponential stability. And for BIBO stability, you can watch the videos. Okay. So basically, the BIBO stability says that uh, if we have a system, okay, so if you have any system, okay, so if you give the bounded input signal, okay, so if you get bounded output signal, okay, we can say this system is stable system. Okay, so what do you mean by bounded input signal? Okay, so if it follows the bounded input or bounded output, okay, so if it follows this definition, what do you mean by bounded here? Bounded signal. Okay, so this is already explained in the video. Okay, so let's say if you take some signal x of t, okay, so and if this is true less than infinity, okay, then we can say for any m, okay, then we can say that system is the signal is bounded. Okay, for example, if you consider x of t is equal to sine t, how does it looks like? It looks like this. Okay, so basically bounded input signal is a signal whose magnitude remains finite over all times. Whose magnitude so remains finite over all the times. Okay, so now here you can see the sine t. So it is bounded between two values. Okay, so it is bounded between this period, right? These two values. Okay, it is finite, correct? So similarly, x of t equal to something like e power minus t. Okay, so this is also bounded. Why? Because it starts at 1, it slowly reduces. This is also finite. Okay, this is bounded sinusoidal, bounded uh, exponential. Suppose if you consider x of t, so this is the bounded. This is also bounded. Okay, suppose if you consider x of t is equal to say uh, t. Okay, how does it looks like t? So this is time versus x of t. Okay, it gets increases like this. Okay, for all the time, this is not finite value. Okay, this is unbounded. Is it clear? So now the BIBO stability says that, okay, if you give the bounded input signal, something like the sinusoidal signal, okay, and if you get the bounded output signal, okay, then we can say that that system is BIBO stable. Is this clear? Any doubt in this?
No, sir.
Yeah. And exponential stability is defined with respect to the poles that we have already discussed in the previous. Okay. So if any pole is existing in the, if all poles are on the left hand side, we will say that that is uh, stable. If any one of the pole is existing on the RHS of S plane, then we can say that it is unstable. Hope this is clear. Okay. Yeah. So now we also have discussed this transfer function extensively. Okay. So where transfer function says that the definition says, so g of s equal to Laplace transform of output by Laplace transform of input with all initial conditions zero. With all initial conditions zero. That's the basic definition of Laplace transform. Sorry, transfer function. Okay. So now we'll enter into this new topic, block diagram representation of the systems.
Sir, here I
Yeah.
have one doubt.
Yeah.
In Bebo's table, the pole locations are
Bibo stable.
pole locations. Like how we can consider the system
No,
is
no.
Bebo's
In
table.
Bibo stable definition, we don't consider the poles location.
Like we consider ROC here. Like, if ROC
Uh,
includes the
no, no.
J
In
omega
here,
axis.
here we don't take the concept of ROC to define the stability. Okay.
But
So
in
Bibo stable and exponential stable both are different. When it comes to LTI systems, both are same.
okay, sir. But
Okay. Um,
in DSP uh, in DSP course they
um,
defined Bebo stability using if the ROC includes the J omega imaginary axis, then it is Bebo stable. Like that. That way.
uh, Maybe the definition could be right. Okay.
Yes, sir.
I'm not quite sure how to connect this BO stable with the poles location. Okay.
Okay, sir.
But I'll try to find the answer.
Okay,
Okay.
sir.
So with the poles location with those. So basically, the ROC is directly connected to the poles. There's no doubt
Yes,
about
sir.
it.
Yes,
Okay.
sir.
Yeah. So block diagram technique. So block diagram representation. So basically, why do we require block diagram? Okay. So basically, if you see any system, okay, so it could be a electrical system, mechanical system, or social system, any kind of systems. Okay. The system is not a single component. Okay. So any system will have combination of number of components, correct? Smaller components, combination of smaller components. Okay, each component, okay, will have its own internal input as well as the output. Okay, so basically this block diagram, it is a pictorial representation. Okay, pictorial representation where each component shall be represented by a block. Each component shall be represented by a single block. Okay, and connect them properly. Okay, so connect them properly. Suppose, for example, you have this. Okay, so let's say you have this input A. Okay, and you are getting a output B. Okay, so and here this system having transfer function of let's say G of S. Okay, so here we could write like D equal to. So what is the transfer function basically? So transfer function says that G of S equal to D by A. Correct? So it means D equal to A G of S. Output is equivalent to input multiplied by the transfer function. Okay. So this same thing we can represent it like this. Suppose we have G. Okay. So you are giving A, correct? And you are getting B. Okay. You're getting B. Okay. So let's say we can write this one like B equal to AZ. Same thing I'm writing. Correct? Okay, so the we'll see different definitions here. Okay, so we'll have three definitions like black, branch point, and summing point. So to represent any system in block diagram representation, so basically we will use these three definitions. We'll learn these three definitions now with respect to this system. Okay, so now here A, correct? So where this is called as the branch point. This is called as the branch point. Okay, and this is called as the block. Okay, now the same thing we can also write it like same thing. If you have two signals A, okay, and let's say I'm giving B here. Okay, so what will I get here? A minus B. Okay, so this is called as the summing point. This is the summing point. Okay, so now let us see. We already know. Is there any doubt in this? Okay, so let me explain you
No, sir.
again. We'll come back here. Okay, so we already know how to write, how to model the system. Okay, so we have seen in the week 1 that the modeling of any system will be in terms of uh, differential equations, correct? So differential equations. For example, consider this. Let's say we have x2 equal to a1 dx1 by dt plus 1 by b integral x1 dt. Okay, this is basically not differential, integro differential. So modeling of any systems we do with we represented as integral differential equations. So this is one example. Now suppose this one, if you wanted to put it in terms of a block diagram, okay, how do we do that? So consider here x1 is the input, okay, x2 is output. Okay, while writing the block diagrams, basically we don't say input and output because we'll have many inputs and many outputs. Instead, we say they are the signals. Okay. So now let us try to put this one in terms of the block diagram. Okay, I'll write it like this. I'll take x1 here. I'll take x2 here because that is the one sides. Okay. Now x1, what we are doing in the first term? In the first term, we are differentiating x1. Correct. So we say that d by dt. Correct. Then we are multiplying with a1. Okay, that is first thing. Next, uh, the second term. Okay, so what we are doing, we are integrating x1. Correct. Again, we are multiplying with 1 by b. Okay, now it is just the addition of these two signals. Correct. So how do we add them? So we add them using the summing point. Okay, this is x2. So now you can see this. From the differential equation, we wrote the block diagram, which can represent the exact same operation. Okay, is this clear? Any doubt?
No, sir.
Okay, so you may see another example. You could write it like let's say x3, because I've already used x1, x2. Let's say a1 x4 plus a2 x5 minus 5. Okay, how can I write this? Okay, so we'll have x4 x5. I need to get x3 here. Okay, so here we can put it like a1. So here you can put it like a2, and so I can take summing point here. Okay, plus. Okay, so this is also plus. Okay. Here I need to get another signal of 5. Okay. This is how we write the block diagrams. Is this clear? Any doubts? Any doubt?
No,
Yeah. So now let us do one thing. We'll take some engineering example. Okay. Uh, so engineering example of so armature controlled DC motor, which all we are familiar with. Okay. So directly I'm writing the differential equations. So I think Sarah has already given these differential equations in the video lecture also. I'm taking the equations. So VA equal to, that is armature voltage, plus IARA, armature current resistance. So LA DIA by T2. Okay. So how we got these equations? Through modeling. So you can check for any textbook. So here modeling is not our aim. The torque, next torque is equivalent to d omega by dt plus d omega. Then back EMF. So kb omega plus finally the angular velocity d theta by dt. Okay, these are the differential equations we have. So first what we do is we start with one by one. Okay, so let's consider the let's say 1, 2, 3, 4, and 5. Okay. So we start with equation 1. Okay. So take the Laplace transform. So take the Laplace transform. Okay. So what do we get? VA of S equal to IA of S RA plus. So what do we have here? LA S IA of S. Okay. So here I'm taking the initial condition 0. Okay. 0 plus EB of S, back EMF. Okay. Is this clear? Any doubts? Okay. Here, so VA of S and EBS of S, they are the inputs. They are the inputs, and IA of S is the output. IA of S is the output. Okay. So now I can write it directly. You can see this from this equation. We can write IA of S directly. So which could be like, so EB of S is back EMF. Back EMF. So these equations we can refer any textbook. Okay, the modeling equations. You'll understand it. Okay. So I of S is, I can write it like VA of S minus EB of S. Okay. So here I take RA common and S IA of S common. Okay. So I'll be taking like RA plus S LA. Okay. I hope this is correct. Okay. So now I can write the block diagram for this part. Okay, I'll write down the block diagram for this part. I'll write it like I said that VA and EB are the inputs, IA is the output. Okay, let me put it. Inputs are VA of S. Okay, EB of S. Okay, output is IA of S. That is how I'll write. Okay, so we wanted to add these two, and this will be a constant. RA plus S LA. Okay, and then I take the summing point plus minus. Okay, so this one and this one. Okay, we'll get this. So what do we get here? VA of S minus EB of S. Clear? Any doubt in this? Any doubt in this?
no, sir.
Yeah. So next, similarly, I'll write here only. So For second equation, if you take the Laplace transform, okay, so you have T of S equal to KT IA of S. So this also we can write it directly. So KT T of S, okay, this will be IA of S. Okay, so similarly, I'll take the third equation. Okay, so third equation, take the Laplace transform. T of S, T of S. So there d omega by dt plus b omega. Okay, that will be like so Js omega of S plus b omega of S. Okay, so here uh, this is input, this is the input, and omega is the output. Okay, so again we can write it like omega of S is what? B, we can take it outside. I can write it like this is T of S, Js plus B, correct? Js plus B. So this also with direct representation. Okay, omega of S, T of S, 1 by Js plus D. Okay, next. So fourth equation is the back EMF, EB equal to KB omega. Okay, so I can write like EB of S equal to KB omega of S. Here EB is the output. Okay, omega is the input. So I can write it directly. Okay, so omega of S, EB of S. Okay, so this is KB. Next, fifth one is the omega is equal to d theta by dt. Okay, so d theta by dt. So we can write it like omega of S equal to S theta of S. Okay, so I can write it theta of S as 1 by S omega of S. Okay, so I can write this as this 1 by S theta of S omega of S. Clear? So now you can see this. I can connect all these things because you have considered individual components, inputs as well as the outputs. Okay, I can connect them. Okay, so first what we have, so this one. So we have this. Let's start with the first equation. Let's start with the first equation. Okay, I can write it here itself. I'm sorry. So I'll take the new one. So
So,
I can write it like this. Yeah. Yes.
before proceeding to it, I have one questions related to the previous slide.
Previous slide. This one.
Yes, sir. Yes,
Okay.
sir.
Yes.
How do we get to know which one is the output and which one is the input? As it's explicitly mentioned in the paper, or we have
No,
to
no, no,
assume
no,
it.
no. It will not be mentioned. Based upon these equations only, we will understand. Okay.
So we have to
Ah, ah.
memorize these
No, 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 no.
equations.
You should not memorize. So when you see your system, suppose for example, okay. So consider it like a government system. Okay. So uh, let us say government having different stages. If you apply for something, okay. So let's say if you are going to register some document, okay. So will you get the direct register sign? No, right?
No, sir.
Yeah. So first you have to give the application. Then there will be some initial check officer. Okay. So he will do that and he will sign the signature. Correct. Then it
Yes,
will
sir.
go to the next officer. It will go to the next officer. So it will have this series. Sometimes what happened is two persons has to check. Okay. Sometimes there will be a loop. Okay. One person after checking it, it will again come to the first stage. correct? So that's the system procedure over there. Am I correct?
Yes, sir.
So there, if you see one component, one a particular person, so he will get the file from his previous officer, correct? And he will pass that file to another officer. There you can easily understand to that particular person who is input and who is output. Okay, that you will understand only once you understand the theoretical aspects of the system. Okay, here the system is your armature control DC motor. Okay, that's why I said uh, see these modeling equations for any textbook. Okay, so but you'll have a global input and you'll have global output. Okay, that you'll understand after writing this block diagram. Okay, so let me write it.
Okay, sir.
Once I put
So
everything,
this
you'll
last
understand.
equation,
Yes, yes, this one.
this, yes, sir. How do you convert it in omega is equals to d theta by
Oh
dt?
yeah, this is
Here the
already
initial
Laplace
condition
transforms
is
now.
zero.
Yeah, yeah. What is the Laplace
Oh,
transform of dx by dt?
no, sir. Just one question. Here
Oh,
the initial condition is zero.
correct.
Okay, sir.
Yeah. So the Laplace transform of this one is s x of s minus x of 0. So here x is the theta. Okay.
Okay, sir.
Initial
Okay.
condition is
Yeah.
0.
Understood. Understood.
Yeah. So now this is the first system. Okay. Now you can see in this system, the output here is IA of S. Okay. Now look for that second block. So second block has IA input, correct? Okay. So now take that system. Okay. So connect it here. Okay. Now you can see this is the IA of S. Okay. Now you can see this. You have output here is PA of S. Check the next one. This one. Okay. Connect it there. Okay. I'll put it here. Okay. Next, what is next system? Uh, I'll move this one in this way. Okay. So what is next system? Omega of S. So this one. Take the next one. Okay. So put it there. Okay. Omega of S. So I'll write this as omega of S. Okay. Here what do we have? We have theta of S. Okay. So what is final equation? Final equation is omega of S. So uh, input and output is theta of S. Correct? So yeah. So omega of S is the input. Okay. No, 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 no. What we are doing here. So J of S. This is not correct. Just a minute. Just a minute. I think I was wrong. So this is the omega of S. Am I correct? Yes. Okay. So next, omega of S. What do we have from this system? 1 by S theta of S. Okay. So from here, what do we have? Omega of S, and it is connected to the input directly. Okay. So I can write it like this. Taking from here, so this one is KB. Okay. So connect here and give this one. So this is your EB office. You can see now. Okay. You'll get the block diagram structure. Every equation will be satisfied. Okay. So the first equation is this one. Okay, first equation is this part. Okay, and then second equation is this part. Okay, and then third equation is this part. Okay, and then uh, fourth equation is this part. Okay, and then final equation, this part. Is it clear? Any doubts? Any doubts? Any doubts?
No, sir.
No, sir.
Okay, so in this way, first your job is to write down the modeling equations. Okay, understand this system, which smaller component is connected to which smaller component. So before and after. So there you'll understand what is input to that block and what is output. Okay. If you have any questions, please do tell me. Now, okay, so previous slide we discussed about the transfer function. Okay, but here there will be a global input. As I said, if you go to the register office, you are giving file to one person. You are the global input. Okay, you don't interfere in the middle steps, correct? The final output is what? Final output is the main register will sign it and give you. Okay, so register sign is the final output. Okay, here also for every system, so sometimes you'll be having the single inputs, or sometimes you'll have multiple inputs also. Okay, so but the transfer function is basically defined with so output versus input. Okay, here basically main thing here output is V of s versus theta of s. Okay, so what is the final output? Laplace transform of output by Laplace transform of the input. Okay, now the question is, since we have this much block diagram, okay, between output to the input, okay, between output to the input is VA of s, output is theta of s. Okay, since we have this much block diagram, okay, how do we find this transfer function? Okay, so that is called as the block diagram reduction. Is this clear? This idea? Okay, so that is called as block diagram reduction. Okay, in the block diagram reduction, what we do is, okay, so let us start with one by one. So we call them as the if two blocks they are connected in cascade, something like this. So Z1, Z2. Okay, individual transfer functions. A system has two components. So each component has its own transfer function. G1 first component, G2 second component. Okay, so this will be, so if you give input A, what do we get here? A Z1. What do we get here? A Z1 Z2. Correct? What is the overall? A Z1 Z2. That is the output. Okay. So finally, what is the equivalent block diagram here? So you'll have A. Okay. So Z1 Z2. I can write it like this. Okay. A Z1 Z2. Clear? So a complex block diagram, uh, so it is not complex, converted to transfer function. What is the transfer function here? So the transfer function here is output. So A Z1 Z2 divided by A input. So transfer function is Z1 Z2. Clear? Okay. Similarly, if you have something like this, okay, so Z2. Okay, let's say where you are giving same thing input V1. Okay, so let's say if you take it like this, plus. Okay, so it is straightforward. So you'll get what? Z1 plus Z2. Okay, so let's say one more thing. So if you have Z, let's say A, You will get AZ here. Okay. Let's say this signal is also A. Okay. Suppose if you want, if your intention is to shift this one here. Okay. We said this is the uh, branching point. Okay. If you wanted to shift that branching point to there, what do we do? So this is very important. So simply what you need to do is start with A. You need to get AZ. Okay. So even after shifting also, the input and output should not change. Input and output should not change. So what do we do? So you take Z, you'll get AZ, correct? So once you shift here, okay, what is the signal I should get? I must get A. Am I correct? The output should not change. But what is the thing I am getting here at this point? AZ, correct? I'm getting AZ. So what do I do to get A?
Divide by.
Divide by
Yes,
Z.
exactly. So add some block here, that is 1 by Z. So that will give you A. Is this clear? Okay. So the output should not change even after reduction also, even after shifting also. Clear? Similarly, you can do the back shifting also. Okay. Suppose another thing is like, let's say you wanted to shift the summing point itself. Let's say we have A, let's say plus plus, you have B here. Okay. So what you get here, A plus B. Okay. Z. Okay. What you get here, A plus B multiplied Z. Okay. Now let's say you wanted to shift this one, this summing point from here to here. From here to here. Okay. So what do we do? Okay. So first you have B here, you have A here. Okay. So you shifted, let us say. Okay. Plus plus. What is the final output you wanted to get? You wanted to get A plus B multiplied G, correct? That is the final output. That should not change. And input signals also should not change. Okay. So what do we do for getting A plus B here? So you take Z here, you take Z here, okay, and add them here. Okay, now you see it has got shifted. Okay. So it is shifting the summing point ahead of the block. Similarly, you can shift the summing point before the block also. You can shift the summing point before the block also. Clear? Any doubt? Okay. So next, the important one. Let's say you have this. You have this simple system. Okay. Plus, minus. Let's say you have this R. Okay. You have G. Okay. Let's say you have C. And simple closed loop system. Hope you remember this concept. Okay. And we have this. Okay. So basically, this is C, correct? This is C. Okay. Now your job is to find what is the overall transfer function. What is the overall transfer function? That is output by input R. Okay. So how can you find that? Okay. So what you can do is you write down the equations first. Okay. So this is a closed loop system. Closed loop system, you know that this is feedback. Okay. Write down the equations. So what are the equations? This will be nothing but CH. Okay. So first, CH, what is this one? This will be like R minus CH. Am I correct? You're getting R positive and CH is negative. Okay. So what will be my C is here? C is G multiplied R minus CH. Correct? C is G multiplied R minus CH. Okay. So I can write this one like RG minus CHG. Okay. So from here I can write this one as C plus CHG equal to RC. Correct? So C, if you take common, 1 plus HG equal to RZ. Okay, so finally C by R equal to what? G by 1 plus GH. Okay, so is this clear?
Yes, sir.
Okay, so suppose if we have plus here, okay, so you'll get C by R as G by 1 minus CH. Okay, so basically we call the plus is nothing but positive feedback. Okay, so minus is for negative feedback. Okay, so what are the examples? Can anybody tell me any example? So negative feedback will be your amplifiers.
Amplifiers and for
Okay,
positive back hysteresis.
positive will be like oscillators. Kindly check that. Okay,
Ischemic trigger.
yeah. Okay, so next, let's take a simple example and try to do the reduction technique. So let's say we have R here, okay, and we have Z1 here, okay, we have Z2 here, okay, and we have summing point here, plus and plus. From here, you are giving another signal Z3 here, okay, let's say C here, and from here you are taking the feedback, H. Okay, now our question is to find what is C by R transfer function. Okay, find C by R. Okay, we cannot find it directly. Why? Because of this point. Okay, so you can see how G1 and G2 are connected. In case if this is not there, they are connected in cascade. Am I correct? They are connected like this fashion. Okay, but that summing point is creating this branch point is creating the problem. So what we do in general is, can anyone tell me what we do? Either shift this point, either shift this point, or shift this point. Okay, so let's do this one. Okay, so shifting. Okay, we wanted to shift that first to that point. Okay, what do we do? So let me write it. This is R. So this is plus and minus. Okay, so we have plus minus. So assume that I have shifted. So V1. So this is H. Okay, so this point. Okay, so this is V2. Okay, here we have plus plus C. Okay, now we wanted to shift. Okay, so what will happen? Shifting point before the point, this one. We are shifting a branching point. So before the block, what do? We do something like this. Am I correct? We do something like this. Okay, so let's do that. So we have shifted here. or we kept it here. Okay, so here we already have another Z3. So after shifting, this will become V1. Am I correct? Okay, so that will be like here we have plus plus. This is C. Now this one. Clear? Any doubt in this? Any doubt in this?
No, sir.
No, sir.
Yeah. Now you could see basically you could see here. So this point. Let me write it here. Okay. So you could see here. I'm sorry. Okay, fine. So you could see this one, this block. So you could see this block. Okay. And then you could see this block. You could see this overall block. Okay. So now can anyone tell me what is this one basically? So this one looks like
True.
negative feedback. Am I correct?
Yes.
Yeah. How do I write that? G1 divided by 1 plus G1H. Correct? This equation. Okay. So the plant divided by 1 plus GH feedback. So same thing I've written. Okay. So what about these two are connected in cascade? So that will be like 1 by Z1 multiplied Z3. Am I correct? Yes or no? Okay. So the
Yes,
last
sir.
one I'll rewrite it later. So first I'll put it like this. Okay. So we have R where this one is Z1 divided by 1 plus Z1H. Okay. Then I have Z2 here and above is 1 by Z1, Z3. Yeah. So Z2 here and they have plus plus C. Okay. Here we have. So Z3 by Z1. This one. Correct? Okay. Now you can see this one. So this will be like two things connected in series. Okay. Sorry, parallel. So this we say what? G2 plus G3 by V1. Am I correct? Okay, so finally, what is the diagram? So we have first one, we have second one. Okay, so V1 by 1 plus G1H. Next one is V2 plus V3 by V1. So this is R and C. Now tell me directly what is C by R is? C by R is the multiplication of these two. Okay, so you will get something like so your denominator is 1 plus G1H and the numerator you'll get is Z1. So Z1, Z2, okay, plus G3. Z1, Z2 plus G3, correct? Yeah, that's the overall transfer function. Clear?
In numerator, we have the G1 multiply by G1 also.
No, no.
Oh, sorry, in denominator. In
Denominator we are
denominator.
getting Z1, no, that both gets cancelled. Numerator we are getting Z1, denominator also Z1, both gets cancelled.
Oh,
Okay, clear? Any questions? Any questions? If you have any questions, so please ask me. Okay, let me try another one. So I'll try another one. Okay, could be like okay, let me try it. So plus minus R. So we have another one plus minus. Let's say Z1. So we have plus minus. Okay. So we have Z2, Z3. Okay. Plus plus. Let's say C. Okay. Can we get some time to solve this? What do you mean? You wanted to solve on your own?
Yes, sir.
Okay, so again, then you can take this as a surprise test. Okay, so you can write it parallel along with me. So H2, okay. So here we have mm, H1, let's say this. I'm getting this. Okay, this is overall feedback. Okay, and we have another one here, Z4. Okay, so that I'm giving as this signal. Okay, I'll go. Yes. So find C by R. So uh, one simple hint is okay. So simple hint is see what you know exactly. That means the reduction techniques. Okay. When things are in cascade, you know how to do. When things are connected like this, so this is basically called as parallel. That is cascade. Okay. This is parallel. Cascade is also called as the series. Okay. So you all think like you know cascade, you know parallel, you know how to shift branching point ahead and before. Okay. And you know how to shift summing point. You know how to do for negative feedback and positive feedback. Assume that these are the things you know. Okay. So now, given the problem, check whether you can apply those techniques directly or not. Okay. If you cannot apply, see what is which branch is creating the problem. Okay. Then try to do the shifting over there. Okay. For example, in this case, okay, basically, where do I start? I'll try to reduce these two. Am I correct? Because they are directly connected in cascade. Then these two are
Yes.
connected in cascade. Okay. Then this entire block. Am I correct? This entire block. Correct? Okay. So this is the first step. So after that, the problem starts. The problem starts here. Okay. That you need to be very careful. Okay. So follow that method and try to do the shifting. So again, the uh, point is before shifting or after shifting, the inputs and outputs should not change. You can add extra blocks so that the cancellation will happen. Is this clear? Here, here,
Oops.
I've added this 1 by Z, okay, for cancelling the effect. That kind of block we can add so that the final output is A. Okay. Yeah. So now note down the entire problem and find C by R. Okay. So this is surprise test. Okay, I hope to took the problem. So I'm closing the call. So as usual, take for 15 minutes by 6:45. So please submit your solutions. So take the image and do mail me. Okay. Yeah. Thanks a lot.